Hey guys, it's Simon and welcome back to the LibGDX RPG tutorial series, where in the last part we learned how to integrate tiled and how to load the different objects with our tiled service and the custom configurator class for Ashley and everything. And we finally had then our play on the screen, also the trees and some other objects which would be available. And what we noticed last time was that the amount of draw calls went up from 1 initially to 6, because for every object that we are rendering right now, as mentioned last time, we need to make a texture binding or a texture swap, because the graphics, the player and the tree are separate graphics at the moment, separate image files. And that's why the rendering process or the rendering pipeline needs to swap those images before rendering, and that requires an additional draw call. And in this part, we're going to optimize that and also make some groundwork for future parts when it comes to animations. And by the end of the part, we should then have a lower number here than 6. I guess it should be 2 or 3. I'm not 100% sure. I think it should be 2. But yeah, that is the optimization that we are going to implement now. So how does it work? The idea behind that is that we use a so-called TextureAtlas, and in very simple terms, what it does, it combines those 3 separate images that we have right here. It combines them into a single image, and then instead of drawing the entire image all the time, we only draw a so-called texture region, so just a specific portion of the entire graphic. That is also what we used in the graphic component. If you remember, we have here a texture region which is used for the rendering process and not an entire texture. And yeah, how can we create a TextureAtlas? So for TextureAtlas, there are a couple of methods available how you can do that. There would be a graphical user interface. If you search for TextureAtlas GUI, you will come to a GitHub repository link, and there you have a standalone application to create the TextureAtlas. I also learned about another online tool. I think it was called Code and Web TextureAtlas, which is also an online tool that you could use. There's also a command line tool available. And yeah, the one that we are going to use in this project, which I think is it's a little bit more effort to set it up, but in the end, I think it's then the fastest approach. And also, if you would use some CI/CD pipelines for your games, or if you always want to repack the images automatically when you start up your game, then the approach that I'm going to show in this part is, in my opinion, the best approach for that. But before we start, we also need to change the LibGDX version, because we need a couple of things in the newest version, which are currently only available in the snapshot. And once the version 1.13.6 is available, which should be, again, soonish, maybe when you watch this video, it's already available, then we have all this functionality available. But right now, we need to use the snapshot version. And I let you know what specific parts we need there. So when we come to that code segment where we use the snapshot functionality. And for now, we need to do a couple of adjustments. So as you know, in the Gradle properties file, there's the GDX version. The latest version currently is 13.5, and we are going to need 6. And at the end, the snapshot version for now. And there was a change in 1.13.5 where the snapshots are not uploaded to the repositories where it was before. So we need to do one additional change, which is not yet part of liftoff. I guess that one is also fixed then in the next liftoff version. But what you have, so when you go to the root build.gradle file, then there is a couple of URLs or online repositories where Gradle tries to find the dependencies. And don't ask me, because I'm also not a Gradle expert, but in this Groovy style format that is used here with GDX liftoff, we have the repositories in the build script. And we also have the repositories for the sub-projects here below. And I simply added the URL to both. areas here. Maybe it's not needed in both areas, but I know that it works when we add it to both areas, so that's why we do that. And the URL that we need, you can also just copy that from the online repository. It's the central Sonatype repository Maven snapshots, and this is how we add that additional address. So whenever when Gradle tries to look up a dependency, then it will also look in that URL address here as well, at that online repository. And we add that here to the sub-projects as well. And now when we refresh our project, we should have the snapshot version available. Okay, so it downloaded a couple of things. Let's start the game. It hopefully still works and looks good. Okay, so we have the snapshot version available. That is the first step. The next step is now that we want to combine our three images into a single texture and using a TextureAtlas. And what I like to do here is that I simply create a new module which can be used for multiple things then in the future. Let's call that, how did I call it in the online repository? I think utils, maybe something like that. And as we learned in the settings Gradle file, we would need to add that here as well so that we have a utils module. And also the utils folder requires a build.gradle file so that Gradle knows that there is something in that which needs to be part of the build process. So let's refresh that quickly. I think an empty build Gradle file should already work. Yes. So the folder icon here has changed. And also in the Gradle integration, we have here our utility module available. Now also here, not to bore you and write down everything one by one, I simply take over the information from the online repository. The important part is the dependencies block. We actually, I think this one, we could remove it. That one I think is also just for Eclipse maybe, not sure. So it could be as simple as that one here. I think to stick to the GDX liftoff format, I copied here everything, all these additional code pieces here as well. But again, the important part is the dependencies section, which means that our utils module, it has access to the GDX jar and also to the GDX tools. So maybe you remember it's in the initial GDX liftoff setup. I did not select the tools, because I said we don't need that. You can download them as standalone versions and things like that. But now in that specific utils module, there we integrate it because we are going to use the TexturePacker tool and call that to pack our textures. Okay, so we have that available. Let's refresh the Gradle project once more. And then we can create the folder already, the source main, Java, yada, yada, yada stuff. Source main Java, then also a package and a class which we call TexturePacker tool. Okay, and in this class we need a main method. And this main method is now simply packing our textures together. So it requires an input directory. So where should it start, or where should it pick up the different image files from? It requires an output directory. So where should it put the result files? And it also requires a TextureAtlas file name. And that should be it. So in the end, what we are going to call is the TexturePacker class here from LibGDX, and we call the process method here, and there we pass in the input directory, the output directory, and the package file name. And that's it. So what I did between those parts, so I created a new folder, as you can see it here, which is called assets raw. And in this raw folder, I created an object folder. And in this object folder, I created the house, oak tree, and player folder and copied the image files there. You can skip the folder, so it is not necessary at the moment to have them available, but that comes in handy in the future when we come to the animation part. So that's why, as a best practice, I suggest that whatever images you have, so for a specific object, put them into a single folder. So the house we put into a single folder, the oak tree into a single folder, and the player, which later on will have a couple of images in it for the idle animation, attack animation, and so on. And all the player-related images are then in the player folder. So suggestion from my side, use one folder per game object. And also we have there this package.json file or this pack.json file, where in some part I mentioned that you can ignore that. But now it is important because what does it do? So when we open up the LibGDX TexturePacker Wikipedia page, I also add the link in the video description below. There is some explanation what it does, how it works, and so on. And there is a specific section, this one here. And this code here, so all the different lines here, simply I copied that into this so-called pack.json file. And for every setting, so let me start again. So every line in this pack.json file is a specific setting for the TexturePacker tool that we are going to call. And every line, so every setting here is then described below here in detail what it does, what kind of values it supports. And for us, I just focus on the most important things that you need to know. So first of all, the padding, which is again the information or a helping tool to avoid the texture bleeding issue that I explained with the tiled map tileset graphic as well. We have, of course, the same issue with TextureAtlas with normal objects. And that's why you should specify a padding when it comes to pixel art. And again, for me, usually a value between 4 and 8 works quite well. Then bleeding, edge padding, and duplicate padding, I would always set them to true, because that also helps then with the texture bleeding issue. POT stands for power of 2. I would also set that to true. It means that the resulting image that gets created, so the combined image, has a power of 2 dimension for the width and the height. And at least back in the days, that was a faster way to send the image to your graphics card. So if the texture was a power of 2 dimension, then it was processed faster than an arbitrary dimension. So power of 2, I would also set that to true. Then you have some specific settings. What should be the minimum size of the resulting texture? What should be the maximum size? And for us, the important part here is the filter for minimum and magnitude, or whatever that stands for. And with pixel art, you always want to have here the nearest option. I think the default option is linear, which works great with normal assets, I would say, which are not pixel art related. But when you have pixel art, then you should use nearest, because if you use linear, then it looks a little bit blurred out, or I don't know how I should describe that. Just try it out. So use the linear filtering and load up your game, and also use the nearest filtering and load up your game. You will notice a difference. And for pixel art, again, the best option is here to choose nearest. And other than that, I think we can say here, combine subdirectories. That's important for us, because we have multiple directories when we pass now our input directory. And I think that's it. These are the most important features for us. Okay, and the input directory. So let me open up the structure again. The input directory would be the assets raw folder. And there we're going to package the objects. The output directory would be the assets folder. And there we create a separate graphics folder. And the file name of the TextureAtlas will be called objects. And that should be it. So let me run this tool, the main method. That was quick. Not sure if it worked. Seems that it worked. So what we got now, as you can see here, we have now one graphic, so one image, the objects.png. That one contains the 3 images that we had before and combined it into a single image. And additionally, we get an Atlas file, which is again some sort of JSON format. And that one defines or describes how big is this image. So it's 256 by 128. What kind of filtering does it use? Then it contains the different images that we have. So for example, the house. And it describes that the house has a size of 80 pixels by 112. And it's located at position 2 and 2. Or the tree is located at position 86 and 51 with a dimension of 41 by 63. So it describes the position and the size of the different original images. And what we get in the end when we load this Atlas in LibGDX, we can then access the different texture regions, as it is called. So the entire image is called the texture, and one specific part of it is the texture region. Okay, so we have now a utils module. As mentioned, you could also use that in your CI/CD pipeline to do something. You could also create Gradle tasks out of that tool so that you can run it via the Gradle integration here as a specific task. I did that for the Masamune project, for example. That's up to you. You can experiment here a little bit around and play with it. For me, since that was a simple project, it was good enough to just call the main method here. And that's it. I think that's a good example of how you can use a separate module in Gradle and how to use a specific LibGDX tool. Good, so now we want to use this TextureAtlas in our game and optimize the rendering. So first of all, since the TextureAtlas is some sort of asset, we need a new asset type. Let's call that AtlasAsset, which implements our asset interface, and it is of type, there's a specific class for that in LibGDX, which is called TextureAtlas. And there we now have an objects atlas where the name is objects.atlas. And again, we have our asset descriptor, and I made the same mistake again. It's not a class, it's an enum. Okay, so we have the constructor. No, that one is wrong. We have the string of the atlas name, and then we have a new asset descriptor, which is located in the graphics folder of our assets folder, atlas name, TextureAtlas. That looks good. And we need the getter. Okay, let's cross-check that once more. So assets folder, graphics, and then objects. Objects. Okay, then we are missing here. Objects.atlas. Okay, yeah, objects.atlas. That looks good. So that should work. Then our asset service can already load such things. And now what we are going to do, we are going to introduce a loading screen. So we don't load this asset or this TextureAtlas just in the game screen. We load it now initially so that we also have here some use cases and an example of a loading screen, which we will enhance later on. And why did I do that? So why should you even add a separate loading screen? I can give you two examples. The first one is if your game runs in the web browser, and imagine your game would start in the main menu where you already play a music for the menu. That will not work in the browser because there is some, I guess it's security, some security stuff that you cannot simply run an audio file when you enter a website. At least this is how it works in the TVM browser. When I made a Kotlin game, what you need to do is that the user makes some interaction on your page. So he needs to press a button or press the mouse button. And after that, you can start playing some music. And that is one good example where a loading screen comes in handy because you can initially load some mandatory assets of your game, for example, a music file. Then the user needs to click to continue. So when the loading is done, maybe you show that in a progress bar or something. And then when he clicks, you can switch to the main menu and then you can start play the music file without an issue. The second example is that later on when we come to Scene2D and some user interface stuff, what you need there is a so-called skin, which defines how your buttons look like, how your dialogues look like, and so on. And this is also a mandatory asset. So before you can even show any user interface related things, you need to load that skin. And that one, for example, also makes sense then to load it in a loading screen so that when we switch then to the main menu screen, we already have the skin available. So that's the reason why we are going to introduce a separate screen here. And this screen here extends the screen adapter class again. And we need access to our game because we need to switch the screen then at some point. And we also need access to our asset service so that we can load the TextureAtlas. And we are going to override the show method. So when the loading screen gets shown, then for all our Atlas assets that we have, we are going to iterate over them. And with our asset service, we are going to queue this asset for loading. So here we are also doing some asynchronous loading process, which we also did not do before, but we prepared already the method in our asset service, and now we are going to use them. But then we have the render method, and in this render method now from our asset service, we call the update method so that the loading of the different assets gets processed. Here you would also do then if you have a progress bar, for example, you get from the update method, you get a Boolean back if it's done or not. And there is also, if I remember correctly, I think a progress or something. Yeah, get progress, a value between 0 and 1, so that you know how much of the loading is already done. So that one you would update here in the render method of the loading screen to indicate to the user how much of the loading is done. Okay, then in here we can add some debug lines. So from our loading screen, we can say finished asset loading. And what we then do here, we create the different screens of our game. That is the first part. Then we remove a specific screen, which is the loading screen itself. We haven't implemented the remove screen method yet. Then we are going to dispose the loading screen because it's just a one-time screen. It's responsible for loading things. And then it's done. We don't need to keep that in memory. And finally, we switch to our game screen. Okay, so create screens for now, it's rather simple. It's from what we have here. Let's remove this line here and put it here. So currently we just have one screen, but in the future there will be multiple screens. For now it's just that one-liner. And the remove screen method, that one is missing. So let me add that here as well. And up here. So what do we need to do? First of all, this is just a generic screen. It's not just a loading screen. And then from our screens cache, we remove that specific class. And that's it. Okay, and finally in our game, so when we start our game, we need to add here the loading screen. That is our initial screen. And we set the loading screen. Okay, so if everything is still working correctly, let's make a check. We should see a debug line, finished asset loading, and we are back to our game screen. So that worked. Perfect. Okay, so finally, we have now a solid groundwork done. So we have, let me recap a little bit. We have the util module available with our TexturePacker tool so that we can combine now the different object graphics into a single bigger graphic, into a so-called TextureAtlas, and then just render the regions out of it. Then we have our loading screen, which is currently loading all the different TextureAtlas assets that we have. And it's then switching to the game screen. And now what we really need to do for the render optimization, we need to update how our entities are created. So we need to go to the TiledAshleyConfigurator, and there we already have this method with the getTextureRegion. And in here, we now need to swap the texture region. We don't use the region that is used in Tiled. Instead, we want to use the region that we have in our TextureAtlas, in the newly created objects TextureAtlas. And so how does that work? A tile needs to define a property which links to the TextureAtlas that should be used. So we will introduce that in a moment, and let's call that AtlasAsset. And by default, it's objects. Wait, let's make it like this. So we have an AtlasAsset objects.name, and that is a string.class. So that is our AtlasAsset as a string. What do I mean by that? So let me open up Tiled and let's go to the objects here. So here, let's also remove these custom properties that we added in the previous part. So let's remove that and let's create a new string property for now. We could also make an enumeration, but for now, to keep it simple, it's just a string, which is called AtlasAsset. And here we say it's objects. Because what we could have, in a real game, we could have multiple texture atlases, maybe one for the different props, maybe one for different objects, maybe one for enemies. And somehow in our game, we need to know to which atlas a specific object belongs. And we link that with this string. So I will create this AtlasAsset attribute now for the other two objects as well. Okay, so we have that available for all three objects. Good. Then the next thing that we need is that we, from our AtlasAsset, we get the enumeration value. So if for whatever reason we made here a mistake and defined an AtlasAsset which is not available in our game, we would get here already an error, because value of will not work. And if you have defined it correctly, then we get the enumeration, which we need then in the next step. So from our asset service, we get the AtlasAsset, which is the TextureAtlas. So this is how everything is then linked together. And now we want to get the specific region out of that. And again, to recap, in the Atlas, so for example, for the player, we know the folder where this graphic is located is the player itself. And the key, or whatever we want to call that after the slash, is currently the file name, which would be, again, it has exactly the same name, but it's actually this file name here. So the house is called house, the oak tree is called oak tree, and the player is the player. So that is the second part after the slash. And the first part before the slash, that's the folder name in our assets raw folder. So this is how this is created together. And now we want to simply get that key out of it. So let's paste that here a little bit, that we have that key here in mind. And here it's a little bit tricky. I can show that in the debugger. I think that makes the most sense. So we know that the tile has a texture region. A texture region is then always linked to a texture. And a texture has texture data, which is a generic class texture data in that case, or it's just an interface. And I know from debugging that this is actually a file texture data. So we need to cast that. And from a file texture data, we can get the file handle. So where to to which file is this texture really linked. And from this file handle, we can get the name without an extension, which would be in our case, for example, player or oak tree. So that would be the Atlas key. Let's call it like that. And finally, from our TextureAtlas, we now want to find a specific region. And currently, this is simply Atlas key, then slash, and then again Atlas key. So it would be player/player, for example. Okay. And if this region is part of our TextureAtlas, then we are going to return it. And otherwise, if it's not available for whatever reason, then we just return the region that was used in tiled, that we render at least something. We could make here maybe some log information that a region was not found or something, that we are aware of that use case. But for now, we just keep it like that. And let me think. Yeah, let me first show you here this texture data here. So let me run the debugger. Unload object. Okay. Okay. So to show it to you here, so we have a tile, which is in that case a static tiled map tile. That one has a texture region. A region is always linked to a texture. A texture is linked to data. And as you can see here, it's a file texture data, which has then a reference to the file itself, which would be in our case maps objects player.png. And if we get this file handle and the name without the extension, as you can see here, we then get player back. And that should be found in our Atlas. Yeah, so I see here we get a TextureAtlas region, and we now return that for our entity. And with that, as you can see, everything is already working great. We reduce the number of draw calls from 6 to 2. Perfect. Why is it 2? So first of all, we have the tile set, the map itself, which gets rendered in the background. That's the first texture binding and the first draw call. And then we render all the different entities, so all the different objects, which now are just part of a single graphic, a single texture. And that would be the second draw call. So we optimized that already quite a bit. Okay, so the last part that I want to show in this part with the optimization is that we are going to update our render system, because at the moment in the update method, we simply render the entire map, which is not ideal because we might have a background in our map and a foreground, and the objects should then be rendered in between. In the example, we don't have that because everything is in the background. We just have a ground and a water tile layer and no foreground here. But in a real game, you will have that something is in front of the normal objects. So that's why somehow we need to know and split up the rendering between background layers and foreground layers. So that is the final step that we are going to do. And how do we do that? So in our render system, we need two separate lists. We need a list of so-called map layer, and we call them foreground layers, and another list which we will call background layers. And initially, those lists are simply empty lists. Okay, then next in our set map method, where we currently just set the map of the map renderer, there we now need to pass what is a foreground layer and what is a background layer. So yeah, let me see. First of all, we need to clear the lists. That makes sense. Then we iterate over the different layers. Okay. If a layer is visible, we are not interested in that. So it seems like that code which was generated here by the auto-completion is again some garbage. What we want to do, we want to know if we are currently adding to the foreground layer list or to the background layer list. So current layers initially we start with background layers. And if objects is equals to our layer name, then we switch it. So then our current layers will be the foreground layers, and we continue. And other than that, so if the layer get class is equals to map layer class, we also ignore it because those are the object layers. We are not interested in rendering them. That's a minor optimization. And other than that, we say current layers at layer. So again, how does that work? So first of all, we say that the current layers, so that the two lists that we have, the background and the foreground layers, we start with the background layers. Then we iterate through those different layers. First, we will get the ground layer added to our background list. Water added to our background list. Then we get to the objects layer. So the name is called objects. So we switch from our background to the foreground layers, because every layer which comes after that is then in the foreground of the objects. That's this swap here. Then this one here, map layer class, those are those layers here. So objects layers are simply called map layers, and we can ignore them because they are not part of our rendering process. And other than that, we add this layer to the current layer list. So with that, we have a split now between background and foreground layers. And the only thing which is left now is to update this method here so that we render entities between background and foreground layers. So how do we do that? First of all, this section here is now the reason why we switched to the snapshot version of LibGDX, because in the map renderer, when we go to the render method again, we need access to the different methods here. So to this render map layer method, which before it was a private or protected method. I cannot remember. So it was not possible for us to call this method. And in the snapshot release, this method changed to a public method. So we can now call it. And that's the reason why we need to switch to the snapshot version. Otherwise, we would need to implement our own patch tiled map renderer with a public method to the render map layer method. And yeah, that is a little bit annoying. And again, in the next LibGDX version, that is anyway fixed correctly. And it's a public method as it is currently in the snapshot version. Okay, so what we need to do, first of all, we need to do animated tile map tile and call this update base time. Where's that coming from? If you remember it, maybe in the begin render method, there we have this line available, which is responsible for the animation update of animated tiles. Then the best practice again, we apply the viewport, and here already we start with our batch rendering. We set the color to a white color. We set the view of our map renderer, and we iterate over the background layers. And from our, how did we call it, map renderer, we call the render map layer method. Then we render our entities in between. So we have the sorting, we have the update. And after that, we reset the color once more, because it could be that the last entity which is rendered here is rendered with a color which is not white. So we need to reset that here correctly. And finally, render the foreground layers. And then we can finish our batch rendering. And that's it. Let's start it once more. I hope we didn't break anything. We still have 2 draw calls. And yeah, that's it. Great stuff. So I'm not sure. Let me check. That part was, again, 40 minutes. It's interesting. I try to keep the parts actually shorter, but I never am able to reach a time below 30 minutes. I hope that's still okay for you. You had some fun and learned quite a few things. That's it for this part. Have a great rest of your day. Thanks for watching, and bye-bye.